So today we're going to talk about different types of compounds. So we're going to use this little Venn diagram we've created to discuss the relationship between molecules. Specifically, when we're talking about organic chemistry, we're often talking about different types of isomers, compounds that are related to each other in some way or another. We're going to use this little Venn diagram to figure out the properties of different types of isomers. So in general, when we're talking about isomers, we're comparing two or more different molecules to each other. They may be isomers if they have some kind of similarity or relationship to each other, right? So iso meaning some kind of similarity. So if we sort of look at molecular relationships, we can have sort of very broad definition, for instance, not isomers, right? So if we have tert-butyl chloride and we have propanol, those two molecules there, definitely not isomer each other. There's not a lot of similarity or relationship between them. Their properties are going to be very different. However, not isomers can even go further. For instance, we have HCl here, we have HBr there. Their chemical properties are pretty similar. Both of them are pretty strong acids, but they don't have the same molecular formula, so they can't be isomers of each other. So having the same molecular formula is a requirement of all isomers. We can go forward and make sort of more broad statements. So for instance, we can create, going beyond not isomers, different types of isomers. We can have constitutional isomers. These are molecules that have different connectivity, but they have the same formula. So for instance, here we've drawn, on one hand here, we've drawn methyl cyclobutane, and then up here we've actually drawn 1-pentene. Okay, these two compounds here have the same formula, right? They're both C5H10. But if we survey the atoms in these molecules, we get very different responses, right? In fact, the one up here would actually say that it's a ring compound, whereas the one up here would say it's a linear alkene. So despite the fact they have the same formula in terms of the atoms present, there may not actually be a lot of relationship beyond that. So when we have that sort of relationship, meaning same molecular formula, but the way the atoms are connected to each other, if we ask the atoms along the chain what they're connected to, if we get different responses, then we're talking about constitutional isomers. And we sort of highlighted them there in blue. Going further, if we have the same connectivity, right? We've got the same atoms connected to each other, we can create stereoisomers, and we've highlighted all different types of stereoisomers here in red. Okay, so this big red triangle that we have there is all the different types of stereoisomers. Two stereoisomers have the same connectivity, meaning every atom along that molecule has the same other atoms connected to it. But the geometric orientation of those can be different, and that's where we get to stereoisomers. There's two types of stereoisomers, or geometric isomers. One of them has a very strict definition, which is the enantiomers, and then if it doesn't fall into the enantiomer category, it's instantly a diastereomer. We've sort of drawn that here with this strict line between the diastereomers and the enantiomers. Two enantiomers are compounds that are mirror images of each other, but are not the same compound, or non-superimposable mirror image compounds. So for instance, here we have two different forms of 2-bromobutane. One of them is the mirror image of the other, and they're non-superimposable. They're not the same molecule. Whenever we have that, we're talking about enantiomers. Two compounds, mirror images, not superimposable. That's very important to note here. Every molecule has a mirror image. It just may be that the mirror image is the same compound as the original one. So for instance, methane and its mirror image are actually the same molecule. But when we have two compounds that are mirror images which are not superimposable, we create enantiomers. When we have stereoisomers, so two molecules, or potentially more, which have the same connectivity but different geometric arrangement, if they are not enantiomers, they instantly become diastereomers. So for instance, we've drawn here the sort of E and Z type alkenes. Those two there are definitely diastereomers. they are not mirror image compounds that are unable to be superimposed on each other. Since they fail that criterion of enantiomers, they instantly become diastereomers. They're still stereoisomers. Or for instance, we've shown these two compounds here. In this case here, down the bottom, both our Cl group and our OH group are in the dashed configuration, whereas up here the OH is wedged or pointing out and the Cl is dashed or pointing back. These two molecules here are not perfect mirror images of each other. They're still stereoisomers, but they're not perfect mirror images. In that case there, these two compounds would be considered diastereomers. So hopefully this little Venn diagram here is helpful to you. Sort of color-coded molecules that are not stereoisomers, so not isomers at all in black, not stereoisomers but constitutional isomers in this blue, stereoisomers in red, and notice here that the things which are enantiomers are completely distinct from the things which are diastereomers. So hopefully we'll sort of have this little Venn diagram, not isomers, constitutional isomers, same formula, not a lot of other similarity. If we have the same geometric, so if we have the same connectivity but different arrangement of the atoms in space, we're talking about stereoisomers. Those can either be enantiomers if they're mirror images that are not superimposable, or diastereomers otherwise. Hopefully that's helpful, and thank you.